if you've got a circle, it says if two inscribed angles intercept the same arc. Okay, reminder from yesterday. You got an inscribed angle. That means that all 3 points of that angle is on the circle. Inscribed. When you're dealing with an inscribed angle, let's say that this arc is a 100-degree arc. Well, what's the measure of the angle? 50. But now look what we've got. What if you've got 2 inscribed angles? And they intercept the exact same arc. Do you see that? The blue angle and the red angle intercept the exact same arc, and you could do it multiple times. You could draw another one. What if you had one up here? Had a green one there. Let's draw a 4th one. What if you had a purple one here? Do you see that all 4 of those angles intercept that exact same arc? Anytime you have an inscribed angle, let's look at the green one. Anytime you have an inscribed angle, that angle will always equal half of the intercepted arc. All 4 of those angles are eating that same 100-degree arc. What's the size of those 4 angles? They're all 50. And that's what this theorem says. If 2 inscribed angles of a circle intercept the same arc or congruent arcs, the angles will have to be congruent. Both of these angles intercept this green arc. So both of those angles would have to be the same measure. We don't have to know what the measure is, but both of those angles would be identical. Any questions? And let me show you something here. Anytime you have this scenario, anytime you have this scenario, let me draw this. Let's draw a black arc. Let's draw a purple one. Wow. And they both intercept that same arc. Do you see that black angle and the purple angle will be the same measure? Let me do it right there. This angle and this angle would be the same size. Yeah, does that make sense? Well, look what else you've got. What's this? Let me do it in a different color here. Let's do light blue. You see that angle? And this angle, red. Look at that blue and that red angle. Do they not intercept the exact same arc right here as well? This angle intercepts this arc, this angle intercepts this arc, so would these angles not always be the same as well? What about these 2 angles? Mm-hmm. You've got this hourglass looking thing. Anytime you have this hourglass inside of a circle, would these angles be congruent? Be careful. Are these 2 congruent? All the angles are the same, so these 2 angles are congruent, right? No, they are similar. Anytime you've got this hourglass shape inside of a circle, you have 2 similar triangles. Sometimes, yes, definitely. If you knew that one side was congruent to another side, for sure, yeah. Maybe these 2 were diameters, and we know the diameters will always be the same every time. They're going to be congruent. You'll have 2 congruent, because then you could do the whole side, angle type things. But anytime you have angle, or in this case, angle, you don't have congruent. You might have congruent, but they're not necessarily congruent, but they are always similar, which means they're proportional. Little piece, over medium piece, over big piece, they're all equal, proportional. So here we go. First problem. Find the measure of angle T. Make it bigger. Find the measure of angle T. Let me point out again, anytime you see an hourglass and y'all know what I mean by hourglass, right? Anytime you see that hourglass type shape inside of a circle, you're going to have this scenario. You've got this purple angle, which is angle T, that's the one you're looking for, intercepts arc VS. You also have this red angle, angle U, intercepts that same arc VS. Anytime 2 angles intercept the same arc, those 2 angles have to be congruent, so therefore, Colton set me up an equation, 3x minus 5. We solve it in our head, we move our x's to the left, we move our numbers to the right. Anybody, what is x? Perfect. We plug it back in just to see. 60 minus 5 is 55 degrees. 40 plus 15 is also 55 degrees. Now, could I go through the process and find the other angles? Probably not. These two angles are 55. Now, I could ask you this. I could ask you, what is arc VS? 110. The angle, the inscribed angle, is always equal to half of the intercepted arc. So if the two angles are 55 apiece, then the angle is going to be, or the arc is going to be 110. Another? Not that one, because that's pretty much the same thing. A proof. This is the proof of what we just told you. If we're given that arc JM and KL is congruent, JM and KL is congruent. Well, maybe not. This might not be identical proofs. We're given here that this arc and this arc is the same. Prove that triangle. Now this is what you just asked me. Will they ever be? Will you ever have the fact that they are, you've got two congruent triangles in there? That's what we're trying to prove. You see your two triangles here. We want to somehow prove that those two triangles are congruent. Somebody remind me. If arcs are congruent, chords are congruent, and what else? Central angles. Y'all remember that? So, but here's the issue. Is that a central angle? We don't know, do we? Is that, is this certain? Now, what if they called it circle N? If they called this circle N, that would mean that N is actually the center of the circle. Then, would there be central angles there? Yeah, but they don't call it circle N. So therefore, we have to assume that N might not be the middle of it. But like you just said, though, let's go through the process here. If the arcs are congruent, then the chords are congruent. So we can't say KL and JM is congruent, which is what they do next, isn't it? JM and KL are congruent because if minor arcs are congruent, their corresponding chords are congruent. Then, let's see, where can we go from there? Because the definition of intercepted arcs, do we know that angle, let me draw here, MJL, you'll see what arc it intersects, and angle MKL are congruent? Yeah. Sure. Do we know that angle, and let me go the other direction with a different color, do we know that angle JMK and angle JLK are congruent? Sure. That's it. Because definition of intercepted arcs. Angle M is what? An angle L, and they are congruent. Inscribed angles of the same arc are congruent. Let's see. Angle M intersects JK. Well, okay. I don't care. You don't have to throw that. For me, that third step's not necessary. Now look what we got, and I don't think we need to go to that next step. We don't even have to go there because look what we said. You've got this angle is the same as this angle. This angle is the same as this angle, and this this chord is congruent to this chord. Are those two triangles congruent? Yeah. By what? Angle side angle. Now they're going to do it different. They're going to say vertical angles are also congruent, and they're going to do like an angle side. But for us, we can say that those two triangles are congruent by angle side angle. Okay. Let's just go through the steps of this. Probably won't have a lot of proofs on your test, if any. Probably none. We're given that QR and ST. QR is congruent to ST. We're also given that PQ and PT. PQ is congruent to PT. And we want to prove that the two triangles inside that circle are congruent. I don't think it's going to be very hard. Dylan B. If QR and ST are congruent, those arcs are congruent, what else is going to be congruent there? Say it again. PQ, now they will be, but not because of what I just said. Let's go ahead and go there. PQ and PT are congruent. If the arcs are congruent, the chords are congruent. And for that same reason, if the arcs are congruent, then QR and ST are also going to be congruent. Is everybody good with that? Now, how in the world are we going to prove the two triangles are congruent? Because right now we have side, side. We need like a side, angle, side, angle, side, angle. We need more information than that. Okay, think about this. Your theorem a while ago stated this. If two angles intercept the same arc, y'all see those two intercept the same arc, then they're congruent. But that's not all it said. If two angles intercept the same arc, or if they intercept congruent arcs. Do you see if these are congruent, the arcs are congruent? What if you've got this angle here, and you've got this angle here? Do those two angles not intercept congruent arcs? So if they intercept congruent arcs, would that not also make them congruent? Look at this. ST, this arc here, is congruent to QR. Does that not make this angle and this angle the same? Same thing here. QP and TP are congruent, so therefore that makes those angles the same. But again, we can't use that because you've got side-side angle, side-side. You can't use sides. That's not one of your ways to prove the two triangles are congruent. But angle what? Angle, side is. Since you have both of those angles, you can say angle, side, angle, side. By angle, side, those two triangles, triangle 1, triangle 2, are congruent. Or you could, what if I wanted to use side, angle, side? Could I use side, angle, side? Because I don't have this angle, do I? Yeah, you'd have to find the top angle. How would you do that? Are those top angles, or the two angles that I'm pointing out there, are they congruent as well? We do. If these two angles are congruent, and these two angles are congruent. The third angle theorem states if you've got two sets of congruent angles and two triangles, then that third set of angles will also be congruent. Okay? So yeah, you could use side, angle, side if you wanted to. I don't know why you'd want to, but you could. Okay, next theorem. Look at this triangle here. Don't read anything yet. This is a diameter. The reason I know it's a diameter is it passes right through the middle there, right through the center. So look at arc FJH. Everybody see arc FJH? How big is it? How many degrees? 180. Your inscribed angle there. Does everybody understand that this angle that I have drawn, this FGH, that is an inscribed angle. The points on the circle, the points on the circle, and the points on the circle. It's like a Pac-Man, like I said the other day. How big is the angle that this Pac-Man is eating? Or how big is the arc? 180. So how big is that angle? This theorem states, and everybody remembers what a semicircle is, right? An inscribed angle of a triangle intercepts a diameter or a semicircle. If this intersects a diameter or a semicircle, if and only if the angle is a right angle, we know why. Because an inscribed angle will always equal half of the intercepted arc. If it intercepts a semicircle, then the intercepted arc is 180. Half of it would have to be 90. So no matter how you draw it, if you've got a circle and I draw a diameter, if my endpoints for my inscribed circle, whether I draw it here, how big is that angle? 90. Or I can draw it here. How big is that angle? 90. Or I can draw it right in the middle. How big is that angle? 90. All three of those, anytime you intersect a semicircle or the endpoints are on the diameter, you've got a 90-degree triangle. Now, of course, if we have a 90-degree triangle, we can use SOHCAHTOA. We can use a squared plus b squared equals c squared. We can go so many different directions with that. So here, you see that scenario. Find the measure of angle F. Find the measure of angle F. Okay, what's going to be our equation here? How big, Jagger, how big is angle G? Look. That's 180, good, so therefore this would be, since it's inscribed to be half of it, it has to be a right angle. Does everybody understand that? So write for me Matt, can you write for me an equation that relates 4x plus 2 and 9x minus 3? What's going to be the relationship between those two angles? Are they equal? This one, let's look at it like this. This angle F intercepts this arc. This angle H intercepts this arc. That's a bigger arc, isn't it? They won't be equal. Can anybody explain to me in one word what the relationship's going to be? You only get one word. Be careful. It's not no, it's not that. It's a C word. Complementary. That's what we're looking for. There we go. Those two angles have to be complementary. When you're in a right triangle, the other two angles have to add up to 90 because the 3 add up to 180. So there's your relationship. So we have 13 x's, and those 13 x's are going to equal 91, right? So x must be 7. Let's test it. If x is 7, that would be a 60-degree angle, and this would be a 30-degree angle. That's fun. So you actually have inside of that a 30, 60, 90 right triangle. And we could go a step further. If on your test I said the distance from here to here is 6, what's the radius of that circle? Diameter is 12, radius is also 6. In a relationship between a 30-60, this was review. Relationship in a 30-60-90, the short side, which here is 6, is always half the half the hypotenuse, which is the diameter. So if this is 6, that would make the diameter 12, which would actually make this 6. And it would also make this 6. And you then have actually a equilateral triangle in there. With wasn't this 60 degrees? 60, 60, and 60, making this 30, making this 30. And you've got an isosceles triangle over here, making that 120 degrees. Man, that makes my head hurt, right? Here we go, moving on. Now let's start inscribing some shapes. Here you've got a quadrilateral. If a quadrilateral is inscribed in a circle, let's stop there and think about it. That's just the if part. If I draw a quadrilateral in a circle, first off, does it have to be like a parallelogram or anything? What do you think? Yeah, it could be a parallelogram. In this case, it's not. That's not a parallelogram. I don't think it's a kite. It kind of looks like one, but I don't think it's a kite. It's not a rhombus. It might. I don't know. Well, no, because these would have to be parallel. I don't think it's a trapezoid. But let's talk about what would be true. And it all is based on inscribed angles. Look at your blue angle. And let's look at our red angle. The red angle intercepts this red arc, does it not? The blue angle intercepts this blue arc. Everybody good with that? When you have an inscribed angle, which both of those, like I said, both of these are, when you have inscribed angles, the angle will always equal half the arc. Now, somebody tell me, the red arc and the blue arc, what's their relationship? These two arcs will add up to what? Do you see the red arc goes from here to here, the blue arc finishes at 360. That red arc and that blue arc must add up to 360 because you've got the whole circle there. So let's do some different scenarios. Let's say the blue arc was, I don't know, 200 degrees, and the red arc is 160 degrees. Does everybody know what type of reasoning I'm using here? Is this deductive or inductive? When I just plug stuff in and look for patterns. Inductive reasoning. What would the red angle be? 80. What's the blue angle? So these two had to add up to 360, right? Isn't that what it said? Since these two angles are half of that, you would think. Let's try another scenario. Let's say that my blue one is 250. That's not 250. There we go. Blue one is 250 degrees. The red one is, that'd make it 110, right? Because they have to add up to 360. How big's my red angle?
55.
55. Because, again, inscribed angle is always half the arc, and that makes my blue angle. What's the relationship? Supplementary. Is it always going to be true? Yeah. And you could actually go a step further and say, well, the purple angle up here intercepts this arc down here. Excuse me. The pink angle right here intercepts this arc. So is the same thing going to be true about my purple angle and my pink angle? Yes. Anytime, and this is kind of cool, that's the reason why. Anytime you inscribe a quadrilateral in a circle, the opposite angles will always be supplementary. Because, again, if you took this angle and this angle, the opposite arcs add up to 360, so the opposite angles would add up to half of that, or 180. So, again, the theorem states opposite angles of a quadrilateral inscribed, that's drawn inside of a circle, would always be supplementary. Like this. You have a necklace here, and it's inscribed in a circle. You have a 90-degree angle. How big is this? 90 degrees. They're always supplementary. And you have 2x minus 30 is your top angle, and x is your bottom angle. They would also be supplementary. Put your x's together. I think so 3 of them. Move the 30 over. That gives you 210, so x must be 70. So this is a 70-degree angle, and that would make this 140 minus 30, which is 110 degrees. What shape is that? It looks like it, doesn't it? I don't know. I'll think about that. Same thing here. When a quadrilateral is inscribed in a circle, opposite angles are supplementary. Dylan C. Opposite angles. That would be angle Z here and not W, right? Those aren't opposite. Those are next to each other. Angle X. Those would be opposite angles. Dylan, if Z is 60 degrees, what's X going to be?
120.
120. Supplementary. So you got a 120-degree angle here. Now, you could use that theorem again, or you could say, you know what, the 4 angles have to add up to 360. Okay, you could do the same thing. I think it's going to be easier just to use it again, right? If this is 95, the opposite angle is going to be 85. Are any of those lines parallel? No. No lines are parallel there, so therefore we don't have a parallelogram, don't have a trapezoid. Y'all remember, right? And that's something you're going to do here as well. If these 2 angles here were also supplementary, those would be same side interior angles, and if they're supplementary, you'd have parallel lines. Okay, here's some more definitions for you. We've already done chord. Here, PR is a chord, and it's actually a special chord called a diameter. PS is also a chord. Okay, a chord is simply a line segment whose endpoints are on a circle. So PR and PS are chords. Is QS? Riley, is QS a chord? No. What is QS? It's a radius. Okay. PR is a diameter. QS is a radius. PS is a chord. PR is also a chord. So that's old definitions. Here's your 2 new ones. A secant and a tangent. Know these. A lot of you will be taking calculus with me probably your senior year. We talk a lot about secants and tangents. A secant line, notice it's a secant line. A chord is a segment. And honestly, a chord and a secant are kind of the same thing. A secant line is a line that hits a circle at 2 different points. It chops it. So do you see that when you have a secant line that you have a chord on the inside there? A tangent line. A tangent line skims a shape. Not necessarily a circle, but any shape. A tangent line will skim it and hit it at only 1 point. That's the difference between a secant and a tangent. Didn't we talk about tangent before? Is there any relationship between tangent lines and sine, cosine, and tangent? You'll learn later. Yes, very possible. But again, secant lines, tangent lines. Secant lines hit the shape at 2 points. A tangent line skims it. And I think I've told y'all before the phrase going off on a tangent. You ever heard that? Well, here's what that means. Like, I do that a lot. If you're talking about something, talking about that same topic, then all of a sudden you start talking about the fair that's coming to town next week. That's going off on a tangent. You just went out in left field. You were talking about something, and all of a sudden you just completely changed subject, and you just went off on a complete tangent in a whole different direction. You see where that? Do you see where that comes from? The term going off on a tangent. Okay, we were talking, then all of a sudden, whoa, there we went. Okay, as you went off in the left field. So you were on the circle, and then you shot off on this tangent line. Okay, going off on a tangent. Okay, that's where that actual statement comes from. So here, tell whether the line or segment is best described as a chord, a secant, a tangent, a diameter, or a radius. Let's go through all these. Carly, AD. Find AD. What is AD? A through C, D. Actually, that's two names. Go ahead and get both of them. It's a diameter, and it is a chord. Since its endpoints are on the circle, it's a chord. Since it goes to the middle, that chord is a diameter. Hunter, CD. Let me erase that. CD is a radius. It is not a diameter. It is not a chord. It is not a secant line. It is not a tangent line. Okay. Now, the AD before, the only thing that made that a chord and not a secant line is, did y'all notice this? It's a line segment. Chords are lines. Okay, tangents are lines. Chords are line segments. Briley, EG is a tangent line. Notice that EG skims your circle, touches it at L, and continues on. It touches it at 1 point and then continues. HB, be careful here, folks. HB, Colton, is a HB is just that part. Do y'all understand why HB is simply that part? You see what's above it? It's a segment. So HB is a chord. Now what is HB? Secant. Okay, if it's a line, if you're talking about the whole line, HB, that goes forever, continues going forever, then it would be a secant. If you're talking about just the line segment, that's a chord. Okay. Here we go. This might make sense to you. If you have a tangent line, if you have a circle and you have a tangent line to that circle, the middle's about right there, and you draw a line, you draw a radius from that center to that tangent line, it will always be perpendicular to it. We're going to use that a lot for the rest of the year. In a plane, a line is tangent to a circle if and only if the perpendicular to the radius is, if and only if it is perpendicular to a radius at the point of tangency. In layman's terms, in plain English, if you have a circle and you've got a tangent line and you draw a radius to that point of tangency to where it's tangent at, it's always perpendicular. Or you can do it backwards. If you draw a line and it is perpendicular to a line here, then that line is going to be tangent as well. So radii and tangent lines, to make a long story short, radii and tangent lines are perpendicular. Y'all see that? Wonder what kind of problems we're going to do now. JL is a radius. Determine whether KL is tangent. We want to know, is KL a tangent line? And a lot of people are saying, yeah, looks like it. The only way that this can be tangent, and like I said, pretty much, yeah, it looks like it. Most of the time with tangent lines, if it looks tangent, it's tangent. Okay, most of the time you're not going to have to go through this trouble. But to make sure that this is tangent, the only way that this can be tangent is if you have a right triangle. question mark. I'm going to put a little question mark in there. Is that a right angle? Is that radius tangent to that line KL? Or excuse me, is that radius perpendicular, making KL tangent? First off, this 9, use common sense, guys. Is the 9 this whole thing? No, it can't be. Right? If it's going to possibly be tangent, 9 is just the distance from here to here. Remember what I told you yesterday? One of the most commonly overlooked things. How far is it from here to here? 8. One word. Radius. If this is 8, then this is 8. So you have 3 side lengths of a triangle here that are 8, 15, and 17. I need to determine, is that a right triangle? If it's a right triangle, then you have a tangent line. 8, 15, 17. If it is a right triangle, Alex, what's going to be the relationship between 8, 15, and 17? 8, Pythagorean theorem. 8 squared plus, finish it for me, would have to 17 squared. But we don't know, right? Let's check and see if it is. Type in 8, somebody type in 8 squared plus 15 squared, somebody else type in 17 squared. 289 on both of them. So therefore, is this a right triangle? Yes. So therefore, is this a tangent line? Yes. That was all just to determine, is that line tangent? Well, it looks like it is. That's another one of the same. We'll go ahead and work it. Maybe this one's not.
8, 15, 17.
It was a triple, wasn't it?
Yeah.
That's the one I told you. The ones I have memorized is 3, 4, 5, and 5, 12, 13. 8, 15, 17. It's rarely seen. Well, I say it's rarely seen. You saw it in that problem. For those of you that had it memorized, yeah, done. You didn't even have to work it out, right? So for those of you that did the extra effort to memorize 8, 15, 17, bam, you're done. What about, let's say the distance from here to here is 8, the distance from here to here is 6, and I'm guessing that's a whole distance there. I wish it had told us. Does it tell us in the problem? Is HL determined? No, they don't tell us. So I'm going to assume that the whole thing is 12. So therefore, to determine, is this a tangent line? If it's tangent, then this would be perpendicular. We're going to do 6 squared plus 8 squared, and we're going to do 12 squared. I don't even have to do it. If you know your triples, 6, 8 goes with what? 3, 4, and 5, doesn't it? If you take 3, 4, 5, and you double everything, it should be 6, 8, and 10. We have 6, 8, 12. Is that going to be a triple? No. This is 100. This is 144. Those are not equal, so that is not perpendicular. So therefore, that would make GH not a tangent line. Looks like one. Now let's do an actual problem. We want to know what X is equal to. You're going to like this. Now on this one, they tell you, and most of them will, they're going to say, okay, JH is tangent, and if you kept drawing it, JH is tangent, GJ is a radius. Anytime you have a radius drawn to a tangent, it's always perpendicular. Anytime you have that scenario, you've got a right triangle. And we know in any right triangle, a squared plus b squared equals c squared. What's the length of your two legs? X and so a squared plus b squared has to equal, this is where it gets fun. What's the length of your hypotenuse? Don't say 8x. 8 plus x. X plus 8. This piece plus this piece. So that's the length of your hypotenuse. A squared plus b squared is equal to c squared. At the first of the year and kind of along the way, we talked about quadratic equations. Anytime you have those squared, more than likely you're dealing with some type of quadratic equation. How in the world do you square x plus 8? And I'm going to put one of these on your test to be prepared. How do you square x plus 8? Y'all remember?
X squared.
Do you do x squared plus 64 to square each piece? Whatever you do. You might want to write this in your note. X plus 8 squared is not equal to x squared plus 64. I deal with this. My first pretty much week of pre-calculus is spent fixing this error. You can't, if you got, this is called a binomial, something plus something squared. If you've got two things in parentheses being squared, you can't square each piece. Now, if you have a single thing in parentheses, you see there's no pluses or minuses there? If you have 8x in parentheses being squared, can I square each piece there? Yes. 64x squared. When you have that plus or minus sign, it throws you off big time. So how in the world are you going to do x plus 8 squared? You do x plus 8 times x plus 8. There's two of them. How do you do that? Does anybody remember the, what you call that? The FOIL, thank you. You've got to do x times x. You've got to do x times 8. You've got to do 8 times x and 8 times 8. FOIL, and a lot of you remember it as FOIL. That's great. You know what FOIL is? The distributive property. It's all it is. What FOIL is you're going to take this x and you're going to distribute it. Then you're going to take this 8 and you're going to distribute it. It's the distributive property level 2, I guess you could say. Take x, multiply it by x. Take x, multiply it by 8. You're done with x. Take 8, multiply it by x. Take 8, multiply it by 8. So you have x squared plus 16x plus 64. FOIL. Remember that? So now, how does that change our problem? We now have x squared plus 12 equals x squared plus 16x plus 64. This problem's not as hard as it looks. Because what happens to the x squared? Because we got to combine like terms. X squared and x squared are like terms. When I move this x squared over and do minus x squared, they cancel. So do you see 16x plus 64 equals 12? Now it's just like what you've been solving. You don't even have to do all that factoring and all that. It's a plain problem. So let's move our 64 over here. So 16x is going to stay. I'm going to do minus 64, which gives you a negative 52. Oh, my bad. Whoops. Thank you very much. You saved me from disaster there. So that'd be 144. I should have went ahead and squared that out. So now when we do minus 64, yeah, that looks a lot better. It gives you 80. So 16x equals 80, so x must be 5. Plug that in. Look what happens. 5, 12, and then that 5 and 8 gives you 13. That's Pythagorean triple. That checks it. Yeah. If you would have noticed that, you could have actually went straight to the answer. Because you know a radius and a radius has to be the same. Now sometimes they'll give you an x here and they won't tell you that that's x as well, and you have to, well, it's also a radius, so it has to be the same. Let's work a couple more of those. Now these aren't as hard as that one. Maybe the second one might be. See, on the second one they didn't tell you that QR is also x. So here we go. On this one, since you have a radius and you have a tangent, you have a perpendicular. We know that a squared plus b squared is equal to c squared. See, that one's a whole lot easier. So how do we find x? Let's type the whole thing into our calculator at once. Let's take 14 squared and move it over. How do I move 14 squared over Dylan B? What does it become when I move it to the right side? And positive or negative, though, when I move it over. See, it's positive here, so yeah, I'm just going to leave it as minus 14 squared. It is 196, good. To get rid of a squared, though, come over here and just square root the whole side. So if you want to type the whole thing into your calculator, the square root is 17 squared minus 14 squared, which is square root of 93. That'd be your exact. Good job. Square root of 93, and I'm pretty sure that's not going to break down. Okay. But that's going to be about 9.6. So about 9.6. If you get an answer bigger than 17, you're wrong. Because we know by looking at that, this is the hypotenuse. Something else we could actually ask you with this problem is how far is it from B to, let's call that point right there, D. How in the world would you find that distance? What? And the radius was, because this was x. If this is 9.6, This is 9.6. So sometimes they'll say, well, what's the distance from here to here? You do the whole 17 minus this 9.6, and that gives you that distance. Okay, the next one. A squared plus B squared equals C squared. They don't give you this length, but we know it's the same as this x. So you have A squared plus, here's your right angle, A squared plus B squared is equal to C squared. This is just like the one we just wrote. And you see what's going to happen again. The x squared and the x squared will cancel. It makes it pretty easy. So you have x squared plus 16 equals, if you FOIL this out and you do x plus 2 times x plus 2, you get x squared plus 4x plus 4. Everybody good so far? When you subtract x squares to get them together, they actually cancel each other out. Jagger, move my plus 4 to the left side. What does the 16 become? Perfect. And since 4x is equal to now 12, x must be 3. We can plug that in, and I bet it's another triple, isn't it? If x is 3 and this is 3, what kind of triangle is that? 3, 4, 5. That's one of your triples. Okay. Let's do one more theorem, and then we're done for the day. My clown hat theorem. It's a dunce cap. Let's see the dunce cap. When you have a dunce cap, you actually have two tangent lines. You'll see those tangent lines. And if you think about this, it's again, geometry just makes sense. If two segments from an exterior point are tangent to a circle, man, that just makes it sound so much harder. If you draw two tangent lines from some exterior point, which in this case was B, the two tangent lines will always be congruent. Always. It just looks like it, right? Because if your dunce cap, if each side of your dunce cap wasn't congruent, it's not going to stay on your head, right? Or clown hat, whatever you want to call it. You put a ball on it and put some circles. Okay, there you go. But anyway, anytime you've got this pointy cap, you've got two tangent lines. The distance from here to here and the distance from here to here will always be the same. That's a pretty easy equation then, right? You've got this circle. You've got tangent line. We know that anytime you have that scenario, that those two tangent distances must be the same. And we can solve that in our head. Matt, move my x's to the left, move my 5's to the right. What is x equal to? 1x and, careful, 20. So therefore that would give me 35 and 35. The distance of each of them would be 35. And this is fixing to run into something we've already done. Look at this. Hey, look, it's a circle that's inscribed in a triangle. How do we inscribe circles and triangles? Yeah, remember those three things we went over called these circumcenters?
Yeah. I think it's like the angle bisectors.
Uh-huh. We went over the circumcenter, the incenter, and the centroid. And orthocenter was in there, but we didn't do orthocenter because it's not as prevalent. To inscribe a circle inside, you find the incenter. And let's talk about how you found each of the three. The circumcenter is where the perpendicular bisectors cross. The incenter was where the wasn't it the angle bisectors? And the centroid was where the medians cross?
Yeah. We didn't want to mid segment.
Well, later on that we talk about mid segments, but not where they, because the mid segments are not going to cross anywhere. Remember, just take a triangle.
It makes it proportional.
Yeah, here's a mid segment. Well, I lost it. Here's a mid segment. Here's a mid segment, and here's a mid segment. See, they don't really cross. But to inscribe a circle in a triangle, you would find the incenter, and the way you would find the incenter is by doing the angle bisectors. But Here's where we're going with this now. So you got this right here. So that's the end center, right? Everybody understand? The end center, you've drawn this circle inside the triangle, so you found the end center and did all that. Well, look what you got now. Is this a tangent line? We didn't present it as a tangent line when we did it the first time, did we? Is this a tangent line? And is this a tangent line? Yes, it is. They all three are tangent lines. It says the distance from here to here is 7. So therefore, would that not make the distance from here to here also 7? And what they're saying here is find the perimeter, I believe. If this whole side is 10, and the distance from here to here is 7, then what's this? What did you just use? The segment addition postulate. Because the whole thing's 10, that's part 7, this is 3. If that's 3, then this is 3 because tangents are the same distance. If this is 3 and this is 8, that makes the whole thing 11, right? But we don't need to know that. If this is 8, then this is 8. So the perimeter would be, you can do it 2 different ways. You can either do 11, 10, and 15. You know what I do, though? I do 3 plus 7 plus 8, and I double it. Because you got 2 of each of them. I believe you get 36 either way.
Yep.
The perimeter of that shape would be 36. And is that connected with the whole in-center stuff? Sure. Let's see, make sure we don't have any more problems of that nature. Yeah, here's another one. Now you got a circle inside of a trapezoid. Clown hat, 3 and 3. 3 and 3. X and X. X and X. Everybody okay with that? Look what they're doing here, though. The perimeter is 18. So the distance around that trapezoid there is 18. Find X. How many 3's do we have there?
4.
So that's 12 plus, how many X's do you have?
4.
Equals 18. Because to find the perimeter, don't you add up all the sides? So 12 plus 4X is 18. We move our 12 over. It gives us 4X is 6, so X must be 1.5. Perfect. What do y'all think? Y'all think that'd be a trapezoid?
Maybe.
Looks like it. Looks like it should be. Opposite sides, left side and right side are both equal to 4.5. Looks to be. Looks like it would be.